Okay, it looks like we're recording here. Yeah, okay, good. So here's what we were talking about last time. We were talking about linear transformations. Again, quick reminder, we've kind of been using linearity a fair amount already at several instances in chapters 1, 2, and 4. So we're here just finally actually getting around to actually defining formally the thing that we've already found a lot of uses for. So quick reminder, a linear transformation is a function. A few requirements. The domain has to be a vector space. The target has to be a vector space. And then lastly, we need to have this linearity condition satisfied. Remember that linearity condition can be expressed in any of sort of three different ways here. Take your pick, they're all equivalent. Okay, so we did a few things with this last time. I talked about different ways that this could kind of show up in the lingo. Right, so heads up about lingo. If someone describes that we have a linear map, okay, that's just a way of saying like something's happening. There's a process. That process could be represented by a function. Maybe we didn't actually formally write it down as such, but there is a process that could be thought of as a function, and that function is a linear transformation. That's what they mean whenever this word linear appears. Okay. And then last thing we did is we actually, brute force directly confirmed a linear transformation. So this function right there from R2 to R2, brute force, we confirmed that you put a linear combination in, you get the expected linear combination out, and it was just, like I say, straight up calculation. Okay, now, linear transformations are wonderful. There's great things you can do with them. We're going to do some surprisingly powerful things with them in this course. You'll see many applications of linear transformations when you get out of Math 216. All of that said, don't make the mistake of thinking that every function is a linear transformation. Sadly, not the case. So an easy counterexample. So a function like this, it's not a linear transformation. You can't just apply the, all of the wonderful properties of linear transformations that we're about to talk about just to any old function. So easy counterexample, right? If this were a linear transformation, these two things would have to be equal, right? Factoring out the two, as it were. But they aren't equal. That's just arithmetic. Just plug in and see. Okay. Now, how do you find these counterexamples? Well, again, no actual, strict formula for how to do that. My intuition on this one was I looked at that term and thought, that's the part that looks to me to not be linear. So let me see if I can generate an example by trying to capitalize on that. How can I sort of get something in there that feels like it ought to be nonlinear? So that's my motivation for making X something that's not zero, so something not linear could have an opportunity to happen. Right? So that's just intuition. Okay. All right. Here's some more linear transformations. Now let me remind you, we're not talking about just functions that happen in Euclidean space. Right? So these could be any function between any vector space and any other vector space. This is an abstract discussion, right? So here's an example. This thing I'm going to call D. We'll talk about how to interpret D in a moment. The domain is, you may remember this vector space. This is a subspace of capital F. This is the collection of all differentiable functions on the interval from A to B. That's my domain. My target is the collection of all real-valued functions. Right? And this linear transformation from that domain vector space to this target vector space, this thing called D, operates as follows. If you give me a differentiable function, the value of D at this differentiable function is the derivative of that differentiable function. And now, of course, if you have a differentiable function, its derivative has to be defined everywhere. Therefore, we have a real valued function. Okay. So this D thing, this abstract linear transformation that we're defining from a vector space of functions to another vector space of functions, It's just the act of differentiating. That's it. You might say it's, I mean, a lot of people would be a little too sloppy and say it's the derivative, right? Do be careful, though, and keep in mind that I'm not saying that all functions that are derivatives are linear functions. That's not at all what we're saying. I'm not saying, well, the derivative of sine x is cosine x. Cosine x is the derivative in that case, and therefore cosine x is a linear. Of course not. Right? That's obviously not true. So you have to keep in mind what am I saying is a linear transformation. I am saying that the act of differentiation is a linear transformation. I'm not saying the result of differentiation is a linear transformation. Everybody see the difference? It's the act of differentiation. Okay, so how would I check directly to confirm that this is a linear transformation? Well, I'm going to take a linear combination of vectors in the domain. I'm going to apply the linear transformation, and with fingers crossed, I hope that what I get out, right, is the expected linear combination of outputs. And at this point, this becomes just a sort of a Calc 1 problem. Whoops, sorry. So we take the derivative. We apply what D is, right? We remember from Calc 1 that the derivative of a sum is a sum of the individual derivatives, and the derivative of a scalar times a function is that scalar times the derivative of that function. All ancient history Calc 1 memories, right? That's nothing tricky happened here, right? And then recall that is the definition of D of F1, and that is D of F2. And so as required, we see that this D is a linear transformation. Is everybody on board with this? Any questions about that? It's a little bit counterintuitive. I mean, you guys did a bunch of differentiating in Calc 1 class, right? And it never probably occurred to you, I assume, certainly didn't occur to me when I was a student in Calc 1, never occurred to me that I was executing a linear transformation. Didn't feel very linear, right? I mean, but again, we're not saying that the results of differentiation are linear. We're saying that the act of differentiation is linear. Okay. All right. Here's another example. Kind of a function that we saw way back in chapter 1, right? Think of a matrix as a function, right? So this gives thinking of a matrix as a function in this way gives nice interpretations of determinant, for example. Don't have time to go through that again, but so this function, I claim, is a linear transformation, and I'm going to leave this as an exercise for y'all to do on your own. Be a nice exercise. It's very, very similar to what we did in the example above. In the example above, you'll notice we had to take advantage of old facts that we already knew about how derivatives work, right? And in doing this one, you're going to have to take advantage of old facts that you already know about how matrix algebra works, right? So details for you guys, good practice problem. If you get stuck, come to my office hours, talk to the TAs in office hours, etc. Okay. I've got several more examples to show you here. Here's a kind of a surprising looking one. In fact, let me zoom in. There we go. Third example. Strange formula I'm about to show you here. If you give me a function that is a C infinity function, remember that this means that the function is infinitely differentiable. Right? If you give me a C infinity function, I'm going to return to you a real number. And here's the formula for that real number. What you're going to do with that function, you're going to take that function and you're going to do an integral from a to b That is the corresponding real number. So you give me a function, I give you a number. That formula. And it does not look linear. Again, we've done a million antiderivatives, integrals, back in Calc 2, I guess, Calc 1, Calc 2. And gosh, that process of taking an integral doesn't seem linear. Lots of weird stuff happens when you take integrals, right? But in fact, it is a linear process. So again, not saying that the result of integration is a linear transformation. We're saying that the act of integration is a linear transformation. Okay, so again, this is something that you guys can do. I'm going to leave this one as an exercise for you as well. I'm about to do another one in just a moment. I'm going to do a slightly harder one than this in just a moment. But it's direct calculation using facts that you already know about integrals. Okay. All right, so here's the one I'm going to do for you. Looks similar. This one's weirder, though. Given a C infinity input function, f, here's how you determine the output value. The output value given that f is you do all of this business. So you there is a fixed function here called g that's part of the definition of this linear transformation. G doesn't change. What you do to the function f is you take your f, you multiply by g, and then you do an integral of the product. That's a linear transformation, unexpectedly. Again, at a glance, it doesn't feel like it, but it's about to work. So this one I'm going to actually do for us. So let me give myself some space here, and we'll crank this one out. Let's see here. I think there's some space up here. Yeah, let's see, so this function, okay, SG, is that right? Okay. All right. Here, let me give myself more space. Okay, so I would like to show that this thing that I've called SG, if I apply this to a linear combination of functions, I would like to show, now I've got some work to do here, right? We'll fill that in a moment. But I would like to show that what I get is C1 S of F1 plus C2 S of F2. That's going to be my goal. All right, everybody recognize? So this is the linearity property that I need to show. Let's see if it works. Okay, so I'm going to say equals with a question mark here. Hopefully, this will work out. Okay. All right, so first let's write down the definition. What is this SG thing? Well, SG says multiply by the fixed function g and then take an integral from a to b. Okay. Following the instructions. We're going to take this C1 F1 plus C2 F2. I'm going to multiply it by g and take an integral from a to b. All right, so this, just writing down the definition of this hopeful, this candidate linear transformation. Yeah, everybody good? Okay, now notice this expression that I have. It's a calculus expression, right? So now I just have to start writing down things that I know about calculus. I mean, flashback memories from Calc 2. And here we go. First of all, I'm going to observe that I can multiply out the interior. This isn't even really calculus. I'm going to rewrite this as C1 F1 G plus C2 F2 G, right? That's just algebra. Now here's a little bit of calculus. I'm going to rewrite this integral as a sum of two separate integrals. This is integral from a to b of C1 F1 G plus integral from a to b C2 F2 G. A little bit of calculus there. right? Old theorem from way back when, that if you have an integral of a sum, that's equal to the sum of two separate integrals. Everybody remember that from way back when? Okay. All right, now here's another thing that I remember from way back when. If you have a scalar factor inside an integral, you can factor that right out. So let's do that. So I have C1 integral from a to b of f1g dx plus C2 integral f2g dx. This, just calculus. Everybody good? And we're basically done, because notice that this is exactly the linear transformation applied to f1. Right? What do we do to f1 here? Multiply by g, do the integral. That's what SG is. And this is the linear transformation applied to f2. So as I was hoping, linear combination in. Oh gosh, what did I just do? I think I hit the thing there. Okay. All right. So linear combination in, linear combination out. It's a linear transformation. Okay. So again, last comment on this, and we'll go on to the next example. I'm not saying that this antiderivative function, that the antiderivative of f times g, I'm not saying that function there, that this resulting function of x is a linear transformation. Certainly not. Right? We're saying that the act, the process that is being applied to f, thought of as a process on f, this process is linear. Okay. All right. Surprisingly important this is going to turn out to be. Okay. A few more examples. This one's pretty. This one's so trivial as to seem pointless, but this is surprisingly important. We're going to make use of this in 353 more so than we will in this course. But if you give me a function, and if I return to you a real value, that real value having been obtained by just plug in x equals 0. Okay, so the act of plugging in x equals 0, this act is a linear transformation. It's a matter of writing it down. We've done a couple of examples here already in class in detail, so I'm going to let you guys work this one out yourself. Right? Good practice problem. Make sure you can do this. If you get stuck, you're not sure exactly how to write it down, come ask me, the TAs, discussion section, classmate, sort of whatever. If you feel like you can write it down, but it just seems like meaningless symbolic manipulation and you're not sure what's going on, definitely ask. Right? But anyway, make sure that you can make sense out of this. Okay. Yeah, question?
Does the same apply if you plug in a different number?
Yes, it does. You can plug in any value. In fact, that's sort of my next example down here. Not only can you plug in any number, you can even, as part of your linear transformation, you can even take derivatives and then plug in any number. Absolutely. So this act of doing to a function, to an appropriately nice function, the act of taking several derivatives and plugging in any fixed value that you like, that act resulting in a real number, that act is also a linear transformation. Yeah, so make sure you can do this one too. Another good practice problem. Okay. All right. And last example, again, this is something we've already talked about, but we've talked about in Chapter 4 these kinds of differential equations. Right? This is a compact way to write the Chapter 4 style, linear differential equations. We made the assertion at the time that they're linear in the sense that, if you put in a linear combination of input functions into there, that you get the corresponding linear combination of the outputs. That's exactly the linearity condition. So you can just flip back to the very first page of our lecture notes for Chapter 4. That algebra that's in there is a proof that this is a linear transformation. Okay, so flip back to there and take a look at that, and make sure you can see the point of view that that's what that's doing. Okay, so that's what linear transformations are. There's a little bit more lingo that we have to set up and sort of groundwork that we have to lay before we can start doing things. So we have to press forward with that. We'll get to the accomplishments soon, right? But groundwork has to get laid. So here we go. Neat theorem about linear transformations. If you pick a basis for the domain, now keep in mind the domain's a vector space. Pick a basis, any basis, it doesn't matter. Pick any basis. If you know the images of those basis vectors, in other words, take those basis vectors, plug them into the linear transformation, see what comes out. That completely determines all of the values of the linear transformation. Okay. Now, that's an outrageous suggestion. Let me give you a quick sort of way to think about that. Let's suppose I were to tell you that we've got some multivariable function, some function here from R2 to I don't know R1, let's say. And suppose I were to tell you, okay, here's E1, and here's E2. Now that makes a basis. Suppose I were to tell you what is the value of f of E1, and suppose I were to tell you the value of f of E2. A couple of values there. Right? That's all I'm telling you about the function. This function here, I'm telling you what f is there. I'm telling you what f is there. Do you feel like you could, therefore, deduce the exact formula for this function? Well, no, of course not. Right? I've only told you the value of 2 points. There's infinitely many points left in the domain that I haven't told you the value of. How could knowing what the function is doing here and there automatically tell you what the function's doing somewhere else? Right? So it seems kind of preposterous. And it is only because of the fact that this condition, the linearity condition of a linear transformation, it's because it's such a powerful condition that we can do this at all. But it totally works, and here's the proof. That's a wonderfully convenient and simple proof. Here we go. Our basis, let's call that list of vectors v1 through vk. That's a basis for our domain here. Right. And let's suppose I have any other vector in the domain. Any vector. Okay, well, that vector in the domain, that's a linear combination of the basis vectors, v1 through vk, by way of, some coefficients here, whatever those are. Don't know what those coefficients are, but we know that those coefficients exist, and we know that they're unique. Right? Okay. All right. Well, by linearity, because this is a linear transformation, I can take this vector, being as it is a linear combination, I can apply the linearity, and note what has come out is, let's see here, I need a little bit more space. By knowing the images of these basis vectors, if I know that, if I know these output values just at the basis vectors, keep in mind I also know these coefficients, right? C1 through CK. You give me some vector V, there's some way, it might be a little bit of trouble to find it, but there is some way to find those coefficients C1 through CK, and therefore I know everything that I need to know in order to compute T of V. T of V is just that formula. Whatever vector you give me in the domain, I can apply linearity, compute the value of the linear transformation, just by knowing the values of the linear transformation on the basis vectors. Yeah, how we doing? Everybody see how this works? Okay. All right, let me show you an example. Okay. So some linear transformation here from R2 to R3. Vector space, vector space. This is a linear transformation. Now our domain is two-dimensional, R2, right? I make the observation that 1, 1 and 1, 2 form a basis for R2. Right, now that's a chapter 1 question. Chapter 2 question. So different ways you can see that. An easy way to see that is these two vectors are not multiples of each other, therefore they're independent, and two independent vectors in a two-dimensional space has to be a basis. So that's a basis. That means that knowing these images here, knowing what the images are of those basis vectors, I'm now going to be able to calculate the value of t anywhere you like. Pick any vector in the domain, it doesn't matter. Now, just as a for example, let me pick this vector here, 3, 4. What's the image of 3, 4? Okay, well, first of all, I've got to write 3, 4 as a linear combination of these basis vectors. Now there's a little bit of a chapter 1 problem there. What are these coefficients that allow me to write 3, 4 as a linear combination of 1, 1 and 1, 2. So if you want to write that down as a little system of equations, whatever, it's effort, but anyway, so something can be done, and you can persuade yourself that there's exactly one way to do it with coefficients 2 and 1. And then, by linearity, linear combination in, linear combination out, I know that is that, and I know that is that, and we have an arithmetic problem at this point, and so t of 3, 4 is that. Everybody see how that works? So, what makes this possible? How is it that I can do this? Well, you really only need two things for this to work. This calculation that we did here, you need to know that every vector that you try to pull this on is a linear combination of your two input vectors. So you need to know that you've got a basis. Right? The other thing you need in order to be able to pull this is you need to be able to, this is where it really happens right here, right? Being able to take t of the input and reinterpret by linearity of t of the individual inputs. So you need to know you have a linear transformation, and you need for your input vectors to form a basis. And this is always going to work. Okay. All right. A little bit more definitions we've got to talk about. Got to define something called a kernel. The kernel of a linear transformation. Now, this is going to seem like a very familiar idea. It really is exactly this. It's almost exactly the same as something we've already talked about. But let me go ahead and define it anyway. The kernel of a linear transformation. It's a subset of the domain. Lives inside of the domain. It is, in fact, here, let me, you'll notice I'm using this set builder notation here. The kernel of a linear transformation is the set of all vectors in the domain, right, that have the property that t of that vector is 0. That's all this says, right? That you can just read it straight off of what's written there. It's the collection of all vectors in the domain whose images are 0. Okay. So now why does that look familiar? Well, because if we were to think, for example, about matrices, right? You can always think of a matrix as a linear transformation. You guys are going to prove that on your own sometime after class, right? The collection of vectors that the matrix multiplies by to give you 0 is the null space. It's an idea that we've already talked about. By the way, the null space is an idea that we already talked. It's the set of homogeneous solutions for that matrix, right? So we already knew that these were the same idea, and now the kernel, as it applies to a matrix, is exactly the same thing. Okay, so why do we have 3 separate words for the exact same vectors? It's because they're not quite exactly the same. The kernel, this is an idea that applies to linear transformations in general, right? The idea null space only applies to matrices. Right, so they're applied in sort of different contexts, but when they overlap, in the situation where you're talking about linear transformations representing matrices, they're the exact same thing. Okay. All right, couple of examples. Here is one of these kinds of functions here, a matrix function. Right? Let's think about this matrix. It's got ones on the, wait a second, it's ones on the diagonal except for it has a 0 down at the end, and then it has zeros everywhere else. So it looks a lot like the identity matrix, but with a critical difference right there. Okay. All right. So, not hard to persuade yourself with a little bit of algebra that T of x, y, z is equal to x, y, 0. Right? So any point, x, y, z, its image is its projection down into the xy plane. So that comes from this algebra, which is just a rewrite of that. Everybody on board? All right. Okay, so what's the kernel? Let's see here. The kernel, recall, the kernel is the collection of all vectors whose image is 0. So there's 0. We're looking for the collection of all vectors, V, such that when you apply this linear transformation, you get 0. We're looking for all the vectors whose projection into the xy plane is 0. So we're looking for the vectors here, like that. Those are the vectors, the z-axis, those are the vectors whose projection are 0. Everybody on board? Okay, yep.
Why is it necessarily the projection into xy plane?
Oh, that's just from the algebra of the function. Let me write that down again. So this formula, I mean, let's just multiply that out, right? This matrix times the vector x, y, z gives us, so the x vector is x, y, z, right? You multiply by that matrix and you get x, y, 0. And you just, geometrically, you can see here the third coordinate 0, that's the xy plane, and the x and y coordinates don't change, so it's projection into the xy plane. Yep. Okay. All right. Here's another example. Now, again, we didn't say it this way at the time quite, but these homogeneous differential equations that we were looking at back in Chapter 4, technically we were looking at kernels. Again, we didn't think of it that way at the time, but it's not that much of a stretch. We've already seen that's a linear transformation. This equation says, looking for when that linear transformation is equal to 0, these vectors in here are the kernel of that linear transformation. Okay, so just a different point of view on stuff we've already talked about. Okay. Moving along. The image. Now, we've talked about this already. I just want to say this again just to have it said. So the image of a function, right? We made a big deal out about that last time. The image of a function, here a linear transformation, is the collection of all vectors in the target with the property that that vector in the target is the image of some vector v in the domain. Right? So, I mean, the set builder notation reads straight just like English. Okay? So said differently, the image here is the collection of vectors in the target that are actual outputs, not hypothetical, allowable, potential outputs, but actual outputs from the function. Okay. All right. So, what is that? Any examples of that? Let's again go back to matrices. Thinking of matrices as functions. What is the image of a matrix thought of as a function? Okay, well, this is a straightforward calculation, brute force calculation. Images, matrix times vector. Right, well, here's how you multiply a matrix times a vector. You take the columns of the matrix. If you want to multiply by some vector here, the coefficients of that vector become the coefficients in a linear combination of those column vectors. Right? That's how you get A times X. That's all the way back to section 1.2, right? One of the several points of view on matrix multiplication that keeps coming up a lot. Okay, so therefore, looking at this result here, the collection of all outputs from this function is the collection of all linear combinations of the column vectors. So remember, these are column vectors. Right? So collection of all of the outputs is the collection of all linear combinations. Now, where have we heard that phrase before? The collection of all linear combinations of the column vectors of a matrix, that's the column space. So this is a nice little result here. We talked back in chapter 2 about the row space and the column space of a matrix, and it seemed like some arbitrary definitions. Things that I guess you could write down for no apparent reason, but why is that interesting? Here's a very crisp answer to the question of why is the column space interesting. Because the column space is the image of the matrix thought of as a function. Right? This is all very natural. If you want to take a matrix, it's very natural to view it as a function. It's very natural to want to talk about the collection of all outputs from that function. It's extremely natural. That's what the column space is. So, kind of ties up a little bit of a loose end for us. That's nice. Okay. Going back to the example on the previous page, remember on the previous page we were looking at that specific matrix. What this matrix does, again, is it kind of projects everything into the xy plane. Right? This matrix thought of as a function is smushing, vertically smushing the function, like smushing vectors like this. Okay. So let's see here. What is the image of this? Well, according to this, the image is the span of the column vectors. The column vectors, you may recall, are 1, 0, 0, 0, 1, 0, and 0, 0, 0. Right, so the image should be the span of those column vectors. And good news, that's exactly what it's supposed to be. Right? You look at these vectors, ask what is the span of these vectors? Well, we don't care about the zero vector. That doesn't affect the span at all. The span of these two vectors, well, we have a vector that way and a vector that way. And the span makes the xy plane. Which, of course, is exactly what we were expecting, right? The image, the result, the collection of all outputs from squishing like that. Oh, come on. Is the xy plane. All right, so in this context here, the kernel of the linear transformation is the z-axis. That's what gets squished down to 0. The image is the xy plane. That's what everything gets squished into. Okay. A couple more exercises for y'all to do. These are pretty straightforward, but these are definitely worth your time. These are kind of mixture problems, so a little bit of chapter 5, a little bit of chapter 2. First one, the kernel is always a subspace of the domain. So subspace, right? So you got to think back to section 2.2. How do you prove something's a subspace? And then apply those ideas to this kernel. Okay. Hint, big hint. We proved something very, very similar to this back in chapter 2. In chapter 2, we already proved that the collection of homogeneous solutions for a matrix is a subspace, right? The kernel is a lot like a collection of homogeneous solutions. Algebraically a little different, but it's morally pretty similar. So look back at the proof where we proved in section 2.2 we proved that the collection of all homogeneous solutions is a subspace. Your proof of this fact will be modeled on that. Okay, good practice problem. Give that a try. Similarly, the image of a linear transformation is always a subspace of the target. Okay, give that a try as well. Okay, as always, I forgot to lower the thing here. Did everybody get the code? Yeah, there it is. I'm going to go ahead and lower this. Okay. All right. Okay. Neat fact. This is in the book. The book proves this fact. I'm not quite going to prove it here. I'm going to do most of a proof here with a promise of the final piece of the puzzle to come later, because it makes the proof an awful lot easier, and I think there's a lot of value in that. You may recall I've done that several times so far this semester. So anyway, here's the statement. If you have a linear transformation where very specifically the domain of the linear transformation is a finite dimensional vector space, and that is important. You need that to be true. So remember what a finite dimensional vector space is, right? Not all vector spaces are finite dimensional, right? C1, for example, is not finite dimensional. Okay. Linear transformation on a finite dimensional vector space, then there is a strong relationship between dimensions. The dimension of the kernel, the dimension of the image, the dimension of the domain, which, again, we know is finite, right? Those add up like this. Okay. All right, now, again, the book has a proof in there, and it's very notation heavy and clunky. I'm going to show you a much streamlined version of that proof. It goes as follows. Don't forget this old fact from chapter 2, right? Do y'all remember this from way back when? You have a matrix. The dimension of the null space plus the dimension of the column space is equal to n, right? The number of columns in the matrix. Weird, right? But there was a reason for this. We in fact we actually wrote down explicit formulas for how to find the dimension of the null space and how to find the dimension of the column space, and it was just a matter of counting that these two formulas for finding bases always made this work. Okay? It's a very sort of directly confirmed fact. Okay, well, this already then proves part of this result. Remember, if you're thinking about linear transformations that are representing matrices, the kernel is the null space, right? The image we just showed is the column space. And of course, let's see here. The domain, what's the dimension of the domain? Well, the dimension of the domain here is n. right? So this thing that we're trying to prove up there, in the special case of linear transformations that are representing matrices, we already know it's true. Right? Okay, so we've proved a special case. That's nice. What does that have to do with the general case? Well, we're going to find in section 5.3, and again, I'm just going to have to ask you to wait until we actually get to it, but it turns out that every one of these linear transformations defined on a finite dimensional vector space, they can all be written as a matrix. So this isn't just a special case. This is all of the cases, as it turns out. Now, I owe you clarity on why it is that every linear transformation on a finite dimensional domain can be written as a matrix. That requires some interpretation. And I'll give that to you in section 5.3. For the moment, let's just work with that and declare this done. Okay. All right. Here's a special case of that theorem. Now, before I get to the special case, I have to remind you of some language. This goes all the way back to single variable calculus. I don't know if you all remember that most Math 216 students have either forgotten this or their single variable calculus classes kind of swept this under the rug. But a long time ago, you had to entertain this question of what does it mean for a function to be invertible, right? So if you want to talk about certain bits of calculus, you want to do the calculus of like arc sine and arc cosine. Y'all remember all that stuff? Long time ago? Well, can you really talk about the calculus of an inverse function if you don't know for sure that a function is invertible? Right? It doesn't really make any sense. You have to know that a function is invertible first. For a function to be invertible, it has to be what we call bijective, which is a word they don't use very much in Calc 1. But all that means, bijective just means what I like to call a perfect pairing. So I'm going to draw you a quick diagram. A perfect pairing from one set to another set. Let's say you have a set with 4 items there. Here's another set with 4 items. A perfect pairing is just any way of sort of pairing them up such that for every output, there's exactly one input. And vice versa. Right? Yes? Well, the target and the image have to pair up. They're not necessarily exactly the same, but they are going to necessarily have a lot in common because of the way that all the elements pair up. Yeah. Yes?
Is one-to-one another word for the same thing?
Tragically, the word one-to-one only means half of this. One-to-one means that for every output, there is at most one corresponding input, which is one of my least favorite choices of words in math, right? One-to-one you would think means perfect pairing, right? Everybody's got a buddy, right? I mean, one-to-one really conjures it, but sadly the word does not mean that. You have to say one-to-one and on-to if you want to use it.
So the difference is...
The difference is that technically we're into discussion of language that's not really critical for what we're doing. How about we talk about this after class? But there is a counterexample. It's just lingo that's more of a distraction than anything else. Yeah, let's worry about it later. So perfect pairing. This is what I want to communicate, right? So a function that is bijective is a perfect pairing where for every output there's exactly one corresponding input. You got this going on. Right? Everybody's got a buddy. Okay. All right. So what this theorem says is that if this is the case, if you have a linear transformation that is bijective, everybody's got a buddy. For every output in W, there is an input in V that corresponds to it, just like this. If that happens, then V and W have to have the same dimension. And it turns out this is a really straightforward proof. I think we should be able to get this done appropriately. Let me just do this real quick. Right? The function goes straight across like that. For every output, there's exactly one input. Let's think about what are the kernel and the image of such a function. Well, if that's the 0 vector, what is the collection of vectors over here in the domain that land on the 0 vector? Well, there's going to be just one of them. It's just the 0 vector. So the kernel is just the 0 vector. What's the image? Well, the image is everything, because by assumption, being bijective, everything in the target, there is a corresponding input value. Everybody's got a buddy, right? So the image is the entire target. We're almost done, in fact. So image is W. So look what this theorem that we already know is true says. That is 0. The kernel is just the 0 vector. The dimension of the 0 vector by itself is 0. The image is W, and therefore, as desired, the dimension of W is equal to the dimension of V, which is what we were trying to prove. Okay, all right. See y'all later. Have a good day. Don't forget about the attendance code right here. Make sure to get this into Sakai before the next 5 minutes.